live on YouTube now. Okay, just more 1 or 2 minutes. So, how big is your department or institute? How many?
Oxford Astrophysics is pretty big. I think it's around 100 people, sort of around 30 faculty, 30 postdocs, and 30 students, roughly, I think.
Yeah, that's pretty big. And
I think Leiden's the biggest in Europe.
Are you in the physics department or astronomy department?
It's the astrophysics is like a sub-department of the physics. It's not a separate thing, but it's like two floors in one of the buildings.
Okay. Is Ian Shipsey is there, right?
He is. He's the head of the whole physics department.
Okay, send my regards to him.
Will do.
He actually gave one of the best webinars in our series. It was
really?
excellent. Yeah,
Sure.
It was very good.
No doubt.
Okay, I think we can start. Yes, Peter, you.
Yeah, I'm ready. Shall I kick off?
Okay, I will just make a short, do a short introduction, and then I will pass you the floor. Okay. Hello, everyone, and welcome to another talk in our webinar series. I'd like to remember that this webinar is also being streamed live on YouTube, and you can find the link on our website, or you can access it on our YouTube channel /LIneA MCTI. Today we have Peter Hatfield from the University of Oxford talking about the relationship between galaxies and their dark matter halos over cosmic time. Peter, thank you very much for accepting our invitation and being with us. The floor is yours.
Okay. Good morning, everyone. It's just 2 in the afternoon here. Thank you so much for inviting me to give a talk. We've got lots of interesting work going on in your various institutions, so thank you very much for inviting me. I'm going to be talking about the relationship between galaxies and their dark matter halos. I'm a research fellow at the University of Oxford, and I also did my PhD in Oxford. So some of this work is my PhD, and some of it is going to be a bit of more recent work I've done. The majority of this was kind of done with collaborators in Oxford, but there's a few other people around the world who are also involved, and most of this is in 4 papers in MNRAS over the last 4 years that I'm going to be talking about today. So what I'm going to cover is just a very kind of quick background of the kind of cosmological scenarios relevant for the research. Then again, I think there's lots of people in this talk who know much more than me about this, but sort of briefly talk about kind of why galaxy surveys are important. Then a little bit about the basics of halo occupation modeling, the kind of main modeling that we did in this data, and then about the kind of actual application to the video survey, and finally what we're going to be looking at in the future. And you can see on the right there, kind of just one of the sort of incredible data sets, kind of seeing a near infrared sky using the Vista telescope in Chile. Each of those dots is a galaxy. The kind of key results to kind of take away from this is sort of you can extract important information about the environment of galaxies from their non-linear clustering, which gives you more information than kind of large-scale linear clustering. You can model this using this HOD model, and our kind of works on that seems to support tentatively mass quenching of galaxy star formation happening at very high redshift, around 6, and then environmental quenching of star formation happening a bit later at more like redshift 1.5. We'll see more of the kind of caveats and what exactly that means later in the talk. So again, I think I suspect everyone in the talk is kind of familiar with the background, but I'm going to briefly discuss kind of our background to cosmology. This is a picture of Oxford there, which we know is on just one planet in just one solar system of the many stars that make up the Milky Way. And the Milky Way itself is just one of many billions and billions of galaxies that kind of make up this cosmic web. So kind of large-scale structure is sort of the physics between the physics of an individual galaxy and the kind of physics of the universe as a whole. So we're kind of, when we're studying large-scale structure, we're kind of trying to understand this web structure. We kind of have this vision of the universe that only a very small fraction of it is normal matter that we're kind of familiar with in our day-to-day life, which we call baryonic matter. And then the rest of the kind of energy content of the universe is made up of dark matter and dark energy, although they're kind of not separated like this in this kind of pie structure. They're obviously all mixed together like that. The kind of reason that we kind of believe in these mysterious things like dark matter and dark energy are kind of understood through a large number of sort of independent ways. We kind of do have good reasons for believing in them. So why do we believe in things like the expansion of the universe? So that's, I'm sure people know, sort of Hubble's law almost 100 years ago was sort of done with standard candles, and then we can kind of do much more sophisticated versions of that these days. We can study things like the cosmic microwave background, and get a snapshot of the anisotropy in the very early universe just after the Big Bang. And then there's kind of several other sort of independent ways to check that we've got a consistent model, so that you can kind of measure, you can kind of probe nuclear synthesis in the early universe by measuring elemental abundances in the universe today. We have observations like the bullet cluster, which I think kind of add to our belief that there really is something like dark matter out there, where the gravitational lensing misaligns from where we think the gas is, and plenty of other things that kind of add credence to our belief that there really is something called dark matter and dark energy out there. So kind of within this vision of the universe we have, because dark matter is believed to be a kind of non-interacting or very low interacting substance, has no pressure, so structure growth in the universe is kind of believed to be dominated by dark matter, and kind of very tiny anisotropies in the very early universe grow under gravity, and we eventually kind of get this web structure that we see today. And in particular, this kind of distribution of galaxies, once they kind of get over a certain density, the kind of growth becomes non-linear. You get kind of individual clumps of dark matter, which we call dark matter halos, which we believe are kind of where galaxies then go on and form after these dark matter halos are formed. So the kind of particular probe of cosmology that I'm going to be talking about is sort of through galaxy surveys. So these kind of deep galaxy surveys are kind of useful for both cosmology as well as kind of understanding how galaxy physics changes over the history of the universe. And in particular, can be talking about 2-point clustering statistics. So that's measuring how clustered galaxies are on the sky, that they're more typically found close to each other. They're not uniformly distributed on the sky. Galaxy surveys typically try and kind of target down to a certain depth, or based on some selection criteria, all the galaxies in an area of the sky. All the work in this talk is kind of imaging surveys, so it's sort of taking very wide, very deep images of the sky. And you can kind of typically use a telescope to look at a wide area, but not go very faint in your detection limit. Or alternatively, you can look at a very small area, go to kind of very faint objects. And kind of as technology improves, you can kind of probe new parts of parameter space. So when this plot was made, kind of technology was along those black points, and then kind of by now we're sort of getting to the sort of purple and red points, and then in sort of another sort of 10 years or so with Euclid and Rubin, we'll kind of be up probing this part of parameter space. So what kind of things in terms of galaxy physics can you do with a galaxy survey? So one of the kind of first things one can do is basically form a stellar mass function. So how many galaxies are there as a function of mass? And if you believe you understand the growth of the dark matter halo structures, you can kind of tentatively make associations with that, and then kind of try and infer what galaxy formation processes are going on to give you that stellar mass function. People, of course, have studied how the star formation rate of galaxies changes over time. So we kind of have this idea that star formation in galaxies today is quite a lot lower than it was in the past. And in particular, most of star formation seems to have happened at more like redshift 1, redshift 2. So the universe today is quite quiet in terms of its new stars. And finally, and the kind of key probe of galaxy physics is understanding the role of environment in it. So lots of people have kind of found that galaxies in more dense environments are less efficient at forming stars, depending on how you're measuring things. So that's just a kind of small number of the kind of ingredients that we're kind of trying to put together to form a cohesive model of galaxy evolution. You can, of course, also use these galaxies as basically tracers for the cosmology. So the 2-point statistics is on large scales telling you the distribution of matter in the universe as a whole. So you can get to take these baryonic acoustic oscillations, which are basically the kind of leftover remnants of sound waves in the early universe. You can kind of measure the power spectrum as a whole, which kind of you can constrain some cosmological parameters with. You can do things like weak lensing. This is kind of the only way you can directly probe the underlying dark matter distribution by measuring how the shapes of galaxies are very slightly altered by gravitational lensing, and how those kind of slight changes in the shear are correlated with each other. And all these things can kind of be used to measure cosmology. So in general, on kind of the small scales of this, we're kind of learning something about the galaxy physics, and on large scales, the distribution of galaxies is telling you something about cosmology. Just to kind of highlight 2 sort of historical instances where galaxy surveys or astronomical surveys have kind of been involved in dramatically changing our cosmological model. In the 60s, when the expansion of the universe was still well cemented from Hubble's law, but there was still some debate about a kind of Big Bang model versus a steady state model. We normally think about the kind of CMB as being the kind of main thing to put the nail in the coffin of a steady state theory, but radio source counts did sort of start to put cracks in steady state model slightly earlier, because in a steady state model, radio sources with a power law spectrum would have a power law sources as a function of luminosity. If you have a universe that doesn't change in time because it's expanding and new matter being created in the gaps, but by then they could kind of tell that radio source counts didn't follow that distribution, which we now interpret as being a consequence of the fact that in the past there were far more bright radio sources than there are in the universe today. So I think the radio source arguments wasn't kind of sufficient to completely rule out, but I think that's quite an interesting example of where these kind of astronomical surveys laid the groundwork for something like the CM to completely rule out the steady state theory. Another more recent one that I think maybe followed a similar structure was for kind of supernovae, giving evidence for the acceleration of the universe and dark energy. The kind of core evidence of that was the sort of 98, 99 supernovae results, but people were showing results from other regions that kind of gave people a reason to believe that omega lambda was not 0. In particular, this plot is from a 1990 paper where omega lambda is 0.8 based on galaxy clustering, and we now think it's 0.7. So another case where sort of like the cracks in the current cosmological model kind of came from galaxy surveys. And of course, last year the Nobel Prize, not specifically for correlation functions per se, but someone who did a lot of the early understanding of galaxy clustering. A 1982 paper there from Davis and Peebles with 2,400 galaxies. And of course, now we can kind of do this clustering sort of millions of billions of galaxies. So it's kind of quite exciting that we're still studying the same things. I'm sure lots of people have got this textbook as well, somewhere on their shelves. So that's kind of what lots of interesting stuff you can do with galaxy clustering. kind of specific kind of regime of clustering that I'm going to be talking about is trying to model this kind of large-scale linear clustering that gives you cosmological information at the same time as your kind of small-scale non-linear clustering that's dominated by information about the galaxy, the environment of the galaxy. So the way we measure this is traditionally done by trying to see how many more galaxies at a given separation you have than you would have by random. So if these are your galaxies in a field, you chuck down a large number of random points, and as a function of angular scale, you measure how many kind of real data points there are at 0.1 degrees versus how many random points there are. And the fact that there's more galaxy pairs than random point separations tells you that they're not uniformly distributed. So what we're kind of trying to probe here is the fact that these galaxies are biased tracers of the underlying dark matter distribution. So this kind of cartoon tries to characterize the linear and non-linear distributions of the dark matter, and then how kind of galaxies form relative to that. So on kind of really large scales, you've got your kind of large modes growing independently, and that's kind of meant to be represented by this kind of dashed line. And then the kind of non-linear halos that have formed kind of meant to be these kind of individual peaks. So the kind of dark matter distribution has the kind of black curvy line. And then say you kind of have a model of galaxy formation that galaxies only form in the densest regions, you'd kind of only see a galaxy in these kind of 3 peaks here. So as the observer, you'd only see those 6 points. You never get to see the dark matter distribution directly. So you can kind of go either say, I want to learn about the underlying dark matter distribution and use your observations of the galaxies to go to that. Or you can say, I'm going to assume that I know the dark matter distribution, observe the galaxies, and then try to infer something about the galaxy physics that led to the galaxies being in that situation. And that's kind of largely the approach that kind of using the HPD way of thinking about things. So we're kind of going to basically assume that we kind of know sufficiently accurately the dark matter distribution, which can kind of be taken from n-body simulations, kind of just dark matter universes. And the kind of 2 particular quantities that feed into this are the halo mass function, which is shown on the left here. So that's number of dark matter halos as a function of mass. So more massive dark matter halos are rarer, and similarly on the right, and also at higher redshift, they get more rare. On the right shows the kind of bias relative to all the dark matter distribution, how much overdense the universe is of those particular things. So a bias of 2 means that if the universe in a kind of individual box was 10% more dense than the average density of the universe, bias of 2 would mean that that box was 20% more overdense, so more overdense of whatever that substance you were talking about. So a bias greater than 1 basically means a more extreme distribution than the global dark matter distribution. And the kind of general trends of that is that higher bias, higher halo mass, and higher redshift. So the general idea of this kind of halo occupation modeling of non-linear structure is that you're going to measure your correlation function from the data, going to generate your kind of model correlation function based on your understanding of the dark matter distribution and how galaxies come to occupy them, and then use MCMC or similar to fit whatever the parameters are that you're interested in. And then you can kind of let free or fix the ones that you believe you know, or the ones that you're interested in inferring. So the kind of ingredients that go into modeling this kind of non-linear galaxy clustering is you need your cosmological model, you need your halo mass function, you need the bias description, so that's the number of galaxies and how clustered the number of halos and how clustered those halos are. You need the underlying dark matter power spectrum. You need the kind of shapes of halos, so what's the kind of density profile of an individual halo. Then probably, at least in this talk, we're kind of interested in the occupation number. So That's what we're kind of actually trying to infer. So that's going to be our unknown. How many galaxies are there as a function of halo mass? So we kind of use a pretty common parameterization illustrated in the plot here. So the kind of 5 parameters are 2 mass scales. So M min is the mass scale required to host a central galaxy. And 1 is the halo mass required to start having satellite galaxies. Alpha kind of describes a power law off to high halo masses, how many galaxies you have. M naught is a halo mass where you don't have any satellites below that. And sigma kind of describes the scatter basically in halo mass to stellar mass. You then need to normally assume that the occupation is Poisson, so it's not always exactly n galaxies, it's a random distribution with average n. People also normally assume that the first galaxy goes at the center of the halo and then subsequent ones trace the profile. And then basically you kind of can combine all these combinations to produce a model correlation function. And people normally think about this in terms of a two halo term being the sort of clustering between halos, so galaxy pairs where one's in one halo, one's in the other, and the one halo term is the sort of clustering of galaxies within one individual dark matter halo. And this is what they kind of look like. So on the left, that kind of shows you the all 4 of those show the same information, just viewed in different ways. So the top is the kind of correlation function in 3D space, and this is the kind of 2 halo part of it, of clustering between different dark matter halos. And you can kind of see a kind of kink as it transitions into the 1 halo term of clustering within individual halos. And then this is the kind of version we'll be using for most of this. You're kind of viewing it in angular space, and again, see on large angular scales, getting the linear effect, and kind of get a transition kind of knee point there. On the right just kind of shows you how the correlation functions vary depending on how those different occupation numbers look. So you can kind of see that as the occupation changes, the correlation functions change in different ways. So you can, by measuring this, you can make inferences on what it looks like. Okay. So the majority of the data I'm going to show, this is from video. This is one of the Vista surveys, PI Matt Jarvis. And we're kind of going to do this by kind of breaking down by stellar mass, star formation rate, redshift, and so on. What this looks like. And video is 3 fields. The kind of published work on this is in 1 square degree, just 1 square degree in the XMM3 field, but we do have the other data for the other 12 square degrees, and hopefully sometime next year we'll be able to kind of put out the correlation functions for the kind of larger degree. So, so far this is just in the published work, it's just 1 square degree. And as well as the kind of near infrared bands from video, there's also CFHTLS optical data. This kind of shows the parameter space that you're able to kind of probe with that, and what kind of stellar masses you can reach down to a 90% completeness threshold. The redshifts are of course not spectroscopic redshifts. These are all photometric redshifts. So again, as I'm sure many people on the call know, kind of you can obviously calculate a redshift by sort of detecting a particular emission line, but then you kind of get very accurate, very confident redshift. But that's kind of very expensive telescope time. So what's actually used is kind of studies like this normally is photometric, which is based on a much coarser sort of 10 or however many photometric bands you have. Those themselves can be done 2 different ways. So you can use template fitting, like kind of have a model SED of what you think kind of galaxy spectra look like, kind of do a kind of chi-squared or equivalent method to kind of get your redshift from that. Or you can also do a kind of machine learning approach where you have a kind of large sample of galaxies where you do know the spectral redshift for, and kind of learn off that, and then make predictions for the galaxies where you don't know the spectroscopic redshift for, based on that. this kind of shows some sample data where kind of the x-axis is the spectroscopic redshift and the y-axis is photometric redshift, and you kind of, if everything's working right, everything's on the line. Unfortunately, it doesn't work as easy as that normally. If you're using a machine learning method, for example, your spectroscopic data probably doesn't probe all of the parameter space as well as you might want it to. So you start to do poorer on ones when you're extrapolating. So this kind of this paper earlier this year, where we kind of explored how bad this were basically by the test data not having the same distribution in color space as the training data, and seeing if you could mitigate against that. So I won't describe in too much detail how we did that, but the kind of top left plot kind of shows the machine learning based methods. If you kind of didn't attempt to mitigate that, so you can kind of see you do pretty well up to about redshift 1.5, but then in the particular setup that we had, you kind of did quite poorly for these ones. One quite nice aspect was at least that we kind of had a method for identifying where the algorithm was extrapolating, so it could at least identify the ones it did badly for, but you'd still be doing quite poorly on these ones, for example, around redshift 2. So the top right figure kind of shows some sort of mitigation that kind of took into account these two different redshift distributions, even though it can't kind of perfectly account for it. So those top two plots are both kind of machine learning based photometric redshifts. The bottom left plot kind of shows your template based predictions of the same galaxies. You can kind of see it has quite a different pattern. So it maybe kind of performs a little bit better at the higher redshifts, but it also kind of gets ones wrong machine learning doesn't get wrong. So we actually found kind of best results kind of hybrids combining the template based and machine learning based. So the bottom right plot shows basically if you use machine learning in the interpolative regime and the template based method in the extrapolation, then overall you get improved results. So it's just worth bearing in mind that these are we're kind of using the photometric redshifts rather than spectroscopic redshifts throughout this. So this is what the correlation functions look like in video, and the kind of corresponding models that we fitted to them. Yeah, again, angular scale on the x-axis and kind of clustering amplitude on the y-axis, and each individual box is a different redshift and a different stellar mass. And some of them it's not obvious, but in some of them you kind of see quite well the sort of transition from the kind of large scale linear clustering to the non-linear clustering. And this is kind of what the kind of halo occupation statistics look like. So x-axis the stellar mass of the galaxy, y-axis is the halo mass. M min is this kind of characteristic halo mass for a halo to start forming a galaxy of that stellar mass. And M1 is your kind of characteristic halo mass for starting to form satellites of that stellar mass. So higher stellar mass is higher halo mass, of course, and you can kind of also start to sort of interpret something to do with the size of the gap. That's kind of telling you something about how easy it is for satellites to kind of stay within a halo, or whether or not they kind of get pulled onto the central galaxy or not. And this is kind of the same data but kind of plotted in stellar mass to halo mass ratio. So halo mass on the x-axis, and on the y-axis is total stellar mass of all galaxy masses divided by the mass of that halo. And you can kind of see kind of reaches a peak of sort of 10 to the 12 and tails off, and then sort of flattens out again as you start to get contributions from the satellite galaxies. So I think what's quite striking about this is that there's, over these redshifts, there's relatively little evolution. This plot shows the halo mass of the peak as a function of redshift from this work and from some other works at the time. There's been quite a lot more people are kind of doing stuff on this, so this probably needs a bit of an update for this plot. But most people kind of think at least that these redshifts stay relatively flat. I think kind of once you start to get out of these redshifts, there's some evidence it changes a little bit more. But at least out to redshift 1, say, it stays relatively flat. You can of course derive kind of any other statistics that one's interested in these. So you can kind of get the large scale linear bias from the HOD model quite easily. but you can also kind of get things like what fraction of the galaxies were satellites, and kind of recover sort of sensible trends like higher mass galaxies have a lower fraction of them are satellites, and at higher redshift there's few satellites as well, which is good. As I kind of emphasized earlier, sort of these are photometric redshifts and stellar masses rather than the kind of true values. So one thing we were kind of quite concerned is to kind of check how much of our results being biased by this. So to kind of test how biased they were, we kind of did a comparison to mock catalogues, also of a square degree in Horizon AGN, which is a hydrodynamical cosmological simulation. There's some colleagues in Oxford and around the world work on. So, and this image on the right there is from Horizon. So we've basically kind of got three catalogues to compare. We've got the real observations, we've got Horizon AGN kind of fake observations, and we've also got the real results inside Horizon. This kind of shows you how well one does on redshift, for example, within the simulation, that how imperfectly you recover the free redshift of the galaxy based on the kind of simulated photometry. And here I kind of did the exact same run of the code that I did with video data on these kind of mock observations from Horizon. And particularly, so this is comparing video observations to Horizon AGN observations. And you can kind of see that the kind of clustering is okay, but is a little bit different. This plot shows, as a function of angular scale, clustering in Horizon divided by clustering in video. And the plot on the right there shows the HOD parameters that I showed a few slides ago. The kind of red yellow points are from Horizon, and the kind of blue green are from video. And in particular, you can kind of see that there's a kind of discrepancy at lower stellar masses. That in Horizon, low stellar mass galaxies are found in lower halo masses than in the real universe. And that's kind of consistent with what people had found in Horizon before, that Horizon overproduces low stellar mass galaxies because they're in lower density environments, basically. So that's comparing kind of real observation to simulated observation. This is comparing Horizon observed to assuming that we had the photometric redshifts and the stellar masses perfect. So it's kind of seeing what's the impact of. Might be having a problem with my Zoom.
Excuse me, Peter.
Right. Yeah, I think you've lost my slides.
Yeah.
Yeah, I'm sure I can get them back again. Sorry about this, folks. Okay. Can you see that?
Yes, we can see your screen again. Thank you.
Awesome. Sorry about that. So this was comparing observations to simulated observations of Horizon. This is now comparing Horizon to Horizon, but one with the observational biases in, and one taking the kind of true redshifts and stellar masses. And you kind of qualitatively get the right answer. The kind of only aspect where I think we kind of seriously biased ourselves was with inferring the scatter on the halo mass to stellar mass relation, where observational biases basically made you overestimate that, because you had weren't taking into account that there was quite a lot of scatter in the estimate of the stellar mass. So those scatters are perhaps better interpreted as kind of including all those. And then finally, kind of this plot just kind of shows, summarizes that. So this is within Horizon AGN cosmological simulation. The black points are the kind of ground truth. So as a function of stellar mass versus halo mass. The green line, the green curves are the kind of ground truth within the simulation. Blue is what you would infer from the clustering if you had the true redshift and the true stellar mass. So that's kind of telling you what systematics are introduced by the fact that you're using this HOD model, and HOD modeling is not itself perfect. And then the red curve is what further biases on top of that you introduce by the fact that you're using observations rather than the real values. So you kind of introduce some kind of bias step. But I think although you do definitely, for example, get this overestimate the scatter and don't get it perfectly, I think kind of hopefully this shows that kind of qualitatively we're kind of recovering the correct even if it's not perfect. So that's all kind of modeling autocorrelations and kind of assuming that halos are kind of perfectly uniform distributed within the halo. One kind of further addition to that we investigated was trying to model the cross-correlation function between two galaxies, between two different samples of galaxies, to kind of tease out kind of interaction between the galaxies inside individual halos. So the cross-correlation function on large scales doesn't give you any extra information because it still just gives you this linear bias, but on smaller scales it does give you different information to the two autocorrelations. So what we were trying to kind of understand is in this kind of cartoon at the top, if the kind of green is the extent of the halo and the stars the kind of center of the halo, and the kind of larger red circle represents some kind of larger galaxy or perhaps an AGN or something, and the smaller dots, blue and red, indicating lower mass galaxies that might be star forming or not forming very many new stars. You can see that different models of how the star formation gets switched off in different parts of the halo are going to impact the kind of small scale clustering in different ways, basically, depending on exactly how it's happening. And so by measuring that, hopefully we can tease apart kind of what scale of an individual halo is relevant to the environment and exactly how it's happening. So this is a bit of a complicated plot, but just kind of shows how that would work. So on the top, there's quenching as a probability of radius. The difference between the lined, the dotted, and the dashed are these kind of three slightly different ways of it working. And basically, kind of see that if you had enough signal to noise in your clustering measurements, you could, in principle, kind of tease out these kind of different radial dependencies within a halo for how things are being quenched. So I think this was kind of pushing the kind of signal to noise by the time you've lit into redshift and stellar mass and specific star formation rate, and trying to do a kind of large number of parameters. But we did do some modeling on this. This is the cross correlation of massive things to lower mass galaxies, and then kind of varying the star formation rate of the low mass things. Red being more passive and blue being star forming. And in particular, you can kind of see that on these plots on the top, where each of these is different redshift bin. For the lower three redshift bins, there was a difference, but for the higher redshift bin, there was essentially no difference, potentially suggesting that there's less of an environmental impact on the star formation of these lower mass things, at least by these redshifts. So that's modeling the cross correlation function. Also at redshift 0.5 to redshift 1.7. And then I think this kind of final bit of the data results is pushing this modeling up to really high redshift. So if you want to go to the sort of really high redshifts, you kind of have to use Lyman break galaxies or Lyman alpha emitters. So rather than sort of having a galaxy where you've sort of detected it in sort of 10 bands, you can sort of do a quite good modeling of the stellar mass and star formation rate and redshift and so on. You kind of have to just sort of detect which bands that you're kind of even detecting it at all in or not based on the Lyman break galaxies. So you can kind of see on this for an SED of an LBG on the top there, for these bands you wouldn't detect anything, and then for these you would see the galaxy. And the bands where that happens is telling you something about the redshift. So this is kind of much more detailed work than what you can kind of get away with at lower redshift. So this was kind of working with a sample of galaxies in a catalogue developed by Rebecca Bowler, also in Oxford, and in work from 2014 and a few other papers first, kind of found that the luminosity function at these very high redshifts didn't drop off as fast as a Schechter function at the higher luminosities, which is kind of interesting. At lower redshifts, the kind of luminosity functions drops off really fast, like this black line, but instead it kind of goes out. You're kind of getting sort of 10 to 100 times as many as you would find for these really brightest redshift 6 objects. So potentially that could be interpreted as when it's kind of indicating that at this redshift you didn't have the kind of mass quenching going on, and objects could kind of grow up to high masses / luminosities very fast. A kind of alternative interpretation is because you're not detecting the stellar mass of these galaxies, you're only detecting their star formation rate. Maybe there's kind of a sort of duty cycle effect going on, and these high luminosity sources are maybe lower luminosity ones, like down here at -20, that are just spending a small fraction of their time up here, because you only have, because the drop off in luminosity is still quite fast. These ones only have to spend a small fraction of their time at a higher star formation rate sporadically to kind of get this effect. So we measured the clustering of these very high luminosity galaxies at redshift 6. There's now very small samples, so you can just about do it. But we did indeed find that they were still much more clustered than these lower luminosity sources. So that suggests that they're not the same source, just caught in different duty cycles of star formation. They are indeed very luminous things in very dense environments. Perhaps, although there's still kind of lots of questions about this, supporting the idea that mass quenching hasn't quite happened there yet. So that's kind of most of the work clustering published to date. Kind of upcoming thing for doing this. One would be that it would be very nice to link to radio data. For example, it's the NEARCAT telescope there out the window. There's radio data covering these fields, so that is something that we're working on. Of course, there's the kind of wider, slightly deeper video data, and of course that was everything up to now was just 1 square degree of it. So we're currently doing the work to extend this to higher redshifts, wider range of stellar masses and larger angular scales and so on. That'll hopefully be out soon. And of course, longer on the horizon is doing all this work in a kind of Euclid plus Rubin plus SKA scenario, where rather than doing it over sort of 1 to 10 degrees, square degrees, would be something like doing it over thousands or over the whole sky, where you'll really be able to get sort of error bars down to essentially 0, break this down into star formation, stellar mass and so on as much as you like, and sort of do justify much more sophisticated HOD models than just assuming the galaxies follow the halo profile. You'll be able to kind of model the kind of interactions in the kind of way that I described with the cross correlation functions. So just to kind of summarize, I've kind of talked about work kind of measuring and then modeling and clustering in the video survey and other kind of related data sets. This is kind of giving you some information about what environment these galaxies are in at the peak of star formation. I've kind of showed you this kind of idea. You can make the HOD model more complicated by introducing kind of quenching mechanisms directly into it. And we also extended this work to higher redshift. where potentially kind of mass quenching stuff can be introduced. The kind of future of this is that you're going to be able to do this to extremely high precision. So you're going to be able to justify more complex versions of HOD modeling. You can do things like redshift space distortions, which this is kind of done at low redshift, but this will be able to go to higher redshift as well if you have spectroscopic data where you can detect the kind of redshift distortions of velocity dispersion of galaxies within halos. And then ultimately, as I say, we're kind of doing this over the whole sky, hopefully in 10 years' time or so. And that's the end of the talk. Thank you very much for listening. Thank you very much for inviting me again. Hope you've all stayed safe during coronavirus. And yeah, be happy to take any questions.
Thank you, Peter, for the very interesting talk. We now have time for questions from the audience. If you joined us on YouTube, you can ask your questions in the comment section, and I will redirect them to Peter. If you joined us on Zoom, you can ask your questions directly. So, questions?
May I?
Sure, go ahead.
Okay, this may sound a bit naive. It's been some time since I don't directly deal with large-scale structure, but you showed that bias between luminous and dark matter is larger at higher redshifts. This is not very easy for me to understand. I mean, if dark matter starts clustering and collapsing, the dark matter structure collapses first, even before recombination, shouldn't it be more clustered in the early stages and then the baryons become more clustered thereafter, more recently, in which case the bias would increase, not decrease? So,
why does the bias of galaxies decrease? I think you may be looking at, was it this one? Was it this graph that a lower redshift?
Yes. At lower redshift, the bias is smaller. So, yeah, I find it hard to understand.
So it's I think that that the halos themselves become less biased. So this shows how in a kind of n-body simulation, the bias of halos as a function of redshift changes with time. So at high redshift, you only found halos in the sort of very densest regions of the universe, and then halos also formed in the less dense regions of the universe at later stages. So my understanding is that the fact galaxy bias decreases over time is a kind of function of the fact that the bias of the halos themselves also decreases with time. So it turns out, kind of these results and kind of other people's similar studies, the kind of stellar mass seems to be relatively, at least over these redshifts, seems to be relatively tightly tied to the halo mass. So it's for a given stellar mass, the fact that the bias changes is mainly driven by the bias of the halos changing. I think you could imagine more complex scenarios where the kind of average halo mass of a given stellar mass bin was changing. So it could kind of, we'd have to see which effect was bigger, but it kind of seems to be the case that for a given stellar mass, the halo mass kind of stays pretty constant, but the bias of the halos decreases. Does that make sense?
So yeah, sort of. It's basically what you're saying. As time progresses, there is a stronger buildup of structure on higher masses, and this makes the
So my understanding is that like at high redshift, there's both far fewer halos, and they are only found in the densest regions of the universe in the kind of terms of the linear structure. But then by lower redshift, you're also getting more halos are formed and more uniformly. So kind of lower.
And you measure the bias relative to that. So
so the bias is relative to that.
Okay.
Yeah, bias is relative to the overall dark matter power spectrum. So there's also the complication that the absolute amplitude of the clustering is increasing, but your bias might be decreasing because you're measuring relative to that rather than the absolute clustering amplitude.
Fine. Okay.
Indeed. I think I've even got a plot of that. So that shows on the left there is galaxies. So the kind of absolute clustering amplitude of galaxies changes relatively modestly, but the amplitude of dark matter clustering changes quite a lot. So the bias changes,
towards the smaller biases between the two, right? Okay. If I may ask another question, I'm not sure if others want to ask, but when you showed that there is a slide with the halo occupation modeling that shows the parameters, including the minimum mass for which a central galaxy is allowed, satellites start building up, and so on. This one. So at the extreme right of this plot, you are already at a galaxy cluster halo mass, say 10 to the 15th solar. So this modeling does not allow for more than one central, but we do see clusters which have more than one central galaxies. Is central here different from what we mean observationally by central galaxies in clusters, where some clusters actually have two of them?
Yes. So
allowing that.
So I guess firstly on the point that it kind of continues up to clusters. When you kind of do all the integrals that go into this, you're effectively multiplying this by a halo mass function. So the halo mass function drops off so fast that the kind of contributions from this end are kind of, depending on what redshift you're on, can end up being quite minor. So you're kind of, most of the clustering is kind of being dominated by the kind of central bit there. So if you kind of, the clustering that I showed at redshift 6, because you're not getting any of the clusters because there aren't any dark matter halos of that mass. I think I kept alpha fixed at that, just because kind of couldn't get any constraining power from the higher mass halos. With regards to the central satellite distinction, all that's meant in this sense is that a central galaxy goes at the center, and that's the kind of first galaxy, if you like, in the halo, and then all subsequent ones kind of trace an NFW, which is kind of a bit simplistic. So what do you mean by observationally a galaxy having more than one central galaxy? What, two BCGs of comparable brightness?
Yeah, that's what I mean. You do see clusters which tend to have, say, 10 to the 15 solar masses with more than one central or very massive galaxy. So, and the model doesn't seem to.
No, I mean, it's like HID is certainly not perfect, and like, for example, I don't think it's again, you probably know more about this in terms of the observations, but I think the assumption that the satellite galaxies follow spherically symmetrically is not perfect. Like halos are kind of ellipsoids, and I think satellites preferentially kind of line a plane, which kind of also violates things. I guess the place that the central galaxy kind of comes in is if you on these plots. So that's the kind of clustering between halos. That's the 2 halo term. Then this term is the clustering of satellites. So that's basically an NFW profile convolved, I think, basically with itself. And then this smaller one is if you convolve an NFW with a point. So basically, if you just had the galaxies tracing an NFW halo occupation, you wouldn't get as much power on the kind of the really smallest scales. So I think that's why kind of people introduced it. But yeah, it's probably not perfect. Sorry, there's a bit of a long answer. I'm not sure it answered. Is that helpful?
Yeah. Okay. Yeah. Sure. Thank you.
But yeah, fundamentally, like, it's quite an idealized system, and like the assumptions are definitely violated. It's whether or not it's kind of acceptable. And like some of the other stuff kind of breaks down. Like I think some people have kind of investigated what happens if you let the Poisson assumption be incorrect and stuff like that.
Okay. Thank you.
Thank you, Basilio. More questions? We still have time. Okay, while we wait for another question, just redirecting from YouTube. Great talk, Peter, from Sidley Lida.
Okay.
I suppose we don't have other questions then. Okay, so let's thank Peter and again. Thank you very much, Peter, for being with us.
Thanks for inviting me.
I'd like to say that this presentation will be available on our website and on LIneA's YouTube channel. For the next week's webinar, we will have Alex Kim from the Berkeley Lab talking about peculiar velocity surveys from the Tweaky Transient Facility, ZTF, and the Ruby Observatory. So thank you everyone for attending, and a special thanks to Peter. Everyone have a great day and see you next week.
Thanks for coming.
Thank you. Bye-bye.